welcome to this problem walkthrough. Today, we'll explore problem number 434, number of segments in a string. In this session, we'll break down the problem, analyze possible solutions, and understand their complexities to equip you with the tools to solve it effectively. Let's dive in. This problem, called number of segments in a string, requires us to count the number of segments in a given string. A segment is defined as any contiguous sequence of non-space characters. For instance, if we are provided with a string S, our task is to return an integer that represents the number of these segments within the string. The input is a single string, and the output is simply the count of those segments. Let's look at an example. If the input string is "Hello, my name is John," the output will be 5 because the string contains 5 segments: "Hello, my name is," and "John." These segments are separated by spaces, which serve as delimiters. In the previous example, the string had clear segments separated by spaces, but let's consider a different input. If the string consists only of spaces, such as, then there are no segments present. The output here would be 0, as there are no contiguous sequences of non-space characters. On the other hand, if the string is simply "hello," with no spaces, the entire string is one segment. In this case, the output is 1 because "hello" is the only contiguous sequence of non-space characters. Now, let's look at another example where the string has leading and trailing spaces. For instance, in the string of course, the output will be 2. The segments here are of n course, and the spaces at the beginning and end of the string are ignored when counting segments. This illustrates an important detail: leading and trailing spaces do not count as segments. Similarly, consecutive spaces between words are treated as a single delimiter and do not contribute to the segment count. Next, consider a string like ABC. In this case, the output will be 3 because the string contains 3 single character segments, A, B, and C. Each of these characters is separated by a space, and since spaces act as delimiters, each character stands alone as its own segment. It's also important to note a few constraints. The string can have a length ranging from 0 to 10,000 characters and can contain a mix of uppercase and lowercase letters, digits, spaces, and special characters. The definition of a segment remains the same: any contiguous sequence of non-space characters. Finally, let's discuss some edge cases. If the input string is empty, such as S equals, the output is 0 because there are no characters in the string, and therefore no segments. Similarly, if the string consists only of spaces, for example, S equals, the output is also 0 since there are no non-space characters. Another edge case involves strings with both leading and trailing spaces, like S equals "Hello World." Here, the output is 2 because the spaces are ignored, leaving the segments "Hello" and "World." Lastly, strings with special characters, like S equals "Hi, how's it going?" are also valid. In this case, the output is 4 because the segments are "Hi, how's it," and "going." These examples demonstrate how the definition of a segment applies across various scenarios. To solve the problem of counting the number of segments in a string, we first considered a brute force approach using iterative parsing. The core intuition here is straightforward: traverse the string character by character, and count segments, which are defined as contiguous sequences of non-space characters. A key part of this method involves using a flag, in_segment, to track whether we are currently inside a segment. If we encounter a non-space character and the flag is set to false, this marks the start of a new segment, so we increment the count and set in_segment to true. Conversely, if a space is encountered, we reset the flag to false, indicating the end of a segment. This approach is efficient in terms of time, with a complexity of O(n), since each character is processed exactly once. Additionally, it has an O(1) space complexity, as we don't use any extra data structures. However, one drawback is the overhead of manually managing the flag, which can make the implementation somewhat verbose and error-prone, especially for edge cases. A second approach leverages Python's built-in split method to simplify the solution. The intuition here is that the split method automatically divides the string into segments based on whitespace, and it handles edge cases such as multiple spaces, leading or trailing spaces, and empty strings effortlessly. The steps are straightforward: we simply call s.split on the string, which returns a list of all non-space segments, and then return the length of this list as the count of segments. The time complexity remains O(n), as each character in the string is processed exactly once by the split method. However, the space complexity increases to OK, where K is the number of segments, because the method creates an intermediate list to store the segments. While this approach is more concise and easier to implement compared to the brute force method, the additional memory usage may be a minor trade-off. Lastly, as a third alternative, we can also use regular expressions to extract all sequences of non-space characters. Using Python's refindAll, our \s+s, we can directly retrieve a list of segments and return its length. This approach is elegant and avoids manual parsing, but it introduces the complexity of working with regular expressions, which may not be as intuitive for all users. The built-in split method emerged as the optimal choice for this problem due to its balance of simplicity and efficiency. A key observation is that split inherently takes care of identifying and counting segments by splitting on whitespace, and it seamlessly handles cases like multiple spaces or empty strings. This eliminates the need for manual flag management, making the implementation concise and less error-prone. The real aha moment here is realizing that the split method's functionality aligns perfectly with the definition of segments in the problem, simplifying the task significantly. While the brute force approach is efficient and avoids additional memory usage, it requires more code and careful flag handling. On the other hand, regular expressions, though elegant, introduce unnecessary complexity for a straightforward problem like this. The primary trade-off with the split approach is its slightly higher memory usage compared to the brute force method, as it creates an intermediate list of segments. However, this extra memory usage is generally negligible for small to moderately sized strings. Overall, the split method strikes the best balance between readability, simplicity, and performance, making it the clear choice. The final solution using the split method has a time complexity of O(n), where n is the length of the string, as each character is processed once. The space complexity is OK, where K is the number of segments, since the split method creates an intermediate list to store these segments. With this understanding, let's take a look at the actual implementation. The code is remarkably concise. We define a function count segments within the solution class, and it simply returns the length of s.split. This one-liner effectively handles all edge cases, including multiple spaces, leading or trailing spaces, and even empty strings, thanks to the robust design of Python's split method. This implementation is not only efficient but also highly readable, making it an excellent choice for solving this problem. To solve this problem, we need to determine the number of segments in a given string. A segment is defined as a contiguous sequence of non-space characters. For instance, in the string hello, my name is John, there are 5 segments: hello, my name is, and John. The brute force approach for this problem involves manually scanning the string character by character to identify where each segment starts. The idea is simple: a new segment begins when we encounter a non-space character that is either at the start of the string or immediately follows a space. By carefully tracking this condition, we can increment a counter each time a new segment is detected. This method allows us to effectively count the segments in a single pass through the string. To implement this approach, we start by initializing 2 variables, count, which will store the number of segments, and in_segment, a flag that tracks whether we are currently inside a segment. Both are initialized to 0 and false, respectively. We then iterate through each character in the string. If the current character is not a space, we check if in_segment is false. If it is, it means we are starting a new segment, so we increment count and set in_segment to true. On the other hand, if we encounter a space, we set in_segment to false, signaling that we are no longer in a segment. This process continues until all characters are processed. Finally, the value of count is returned as the total number of segments in the string. Understanding the key insights behind this approach is crucial. First, a segment is defined as a contiguous block of non-space characters, which means a segment starts only when a non-space character is preceded by a space or is at the very beginning of the string. To efficiently track these transitions, we use the in_segment flag. This flag helps us detect when we enter or leave a segment. It's also important to handle edge cases, such as an empty string, which has 0 segments, or a string with only spaces, which also results in 0 segments. Similarly, strings with leading or trailing spaces should ignore those spaces and count only the actual segments. The time complexity of this algorithm is O(n), as we process each character exactly once, while the space complexity is O(1), since we only use a few variables. In terms of data structures, this approach relies on two simple variables, count and in_segment. The count variable keeps track of the total number of segments, while the in_segment flag indicates whether we are currently inside a segment. This simplicity ensures minimal space usage, as no additional data structures like arrays or lists are required. To better understand how the algorithm works, let's walk through an example. Consider the input string hello, world. By processing this string step by step, we'll see how the algorithm detects and counts segments. We begin by initializing count to 0 and in_segment to false. Next, we start iterating through the string. The first two characters are spaces, so in_segment remains false, and count does not change. When we encounter the character h, which is non-space, and in_segment is false, we recognize the start of a new segment. We increment count to 1 and set in_segment to true. The following characters, e, l, and o, are all non-space, so we remain in the same segment. When we encounter another space, in_segment is set to false, signaling the end of the segment. Later, when we reach the character w, another non-space character, and in_segment is false, we detect the start of a new segment. We increment count to 2 and set in_segment to true. This process continues until the end of the string. The final value of count is 2, indicating that there are 2 segments in the string. While the brute force approach is efficient and works well for this problem, we can consider some minor optimizations. For instance, if the string is empty, we can immediately return 0 without further processing. Additionally, we could pre-process the string to trim leading and trailing spaces and split it by spaces to count segments directly. However, this would increase space complexity due to the creation of intermediate data structures. Overall, the brute force method strikes a good balance between simplicity and efficiency, making it a solid choice for solving this problem. This solution implements a function to count the number of segments in a given string. A segment is defined as a contiguous sequence of non-space characters. The count segments function uses a single loop to process the string character by character. First, we initialize count to 0, which keeps track of the number of segments, and in_segment to false, which acts as a flag to indicate whether the current character is part of a segment. The function then iterates through each character in the string. If the character is not a space, we check if we are currently outside a segment, not in_segment. If true, this marks the start of a new segment, so we increment count and set in_segment to true. If the character is a space, it signifies the end of the current segment, so we reset in_segment to false. By the end of the loop, count will contain the total number of segments in the string. This approach is efficient, as it only requires a single pass through the string, O(n), time complexity, and does not use any extra data structures, O(1), space complexity. This ensures the solution is optimal for both small and large inputs. This is the Java implementation of LeetCode problem number 434, number of segments in a string. The logic mirrors the provided Python solution, with key differences being the use of Java's charat to access characters in the string, along with explicit type declarations for variables. The method iterates through the string, maintaining a flag, in segment, to detect transitions between segments and whitespace. The solution is efficient and concise, adhering to Java conventions. To solve the problem of counting segments in a string, let's start with example 1, where the input is s equals hello, my name is John. Initially, we set up two variables, count, which tracks the number of segments, and in_segment, which indicates whether we are currently inside a segment of non-space characters. Both are initialized to 0 and false, respectively. Now, as we iterate over the string, the first character we encounter is h, which is not a space. Since we're not currently in a segment, in_segment equals false, we start a new segment, incrementing count to 1 and setting in_segment to true. For the next characters, e, l, o, all of them are non-space characters, and since in_segment is already true, we stay in the same segment. When we encounter the next space character, we end the current segment by setting in_segment to false. After the space, the next characters are m and y. These are non-space characters, and since in underscore segment is false, we start a new segment, incrementing count to 2 and setting in underscore segment to true. This process is repeated for the remaining words, name, is, and John. Each time we encounter a non-space character following a space, we recognize the start of a new segment and increment our count. By the end of the string, we have identified a total of 5 segments, and the output is 5. Now let's examine example 2, where the input is s equals hello world. Again, we initialize count to 0 and in underscore segment to false. The string starts with several spaces, so as we iterate through these characters, in underscore segment remains false because spaces do not indicate the start of a segment. Eventually, we encounter the character h, which is not a space. Since in underscore segment is false, we start a new segment, incrementing count to 1 and setting in underscore segment to true. As we process the rest of the word hello, we remain in the same segment because in underscore segment is true. Afterward, we encounter another series of spaces, which ends the current segment, so we set in underscore segment to false. Next, we reach the word world. When we encounter the first character, w, it's a non-space character, and since in underscore segment is false, we recognize the start of a new segment. We increment count to 2 and set in underscore segment to true. As we process the remaining characters in the word world, in underscore segment remains true, indicating that we are inside the same segment. Finally, the string ends with trailing spaces. These characters do not indicate the start of a new segment, so in underscore segment is set to false. In this case, the total number of segments is 2, and the output is 2. Lastly, let's consider example 3, where the input is an empty string, s equals. Here, we initialize count to 0 and in underscore segment to false as usual. However, since the string is empty, there are no characters to iterate through, and the loop does not execute. As a result, the total number of segments remains 0, and the output is 0. This example highlights that an empty string contains no segments by definition. The time complexity of this algorithm is O(n), where n represents the length of the input string. Let's break this down mathematically. The algorithm uses a single for loop that iterates through each character in the string exactly once. For every character, the operations performed are constant time operations, checking whether the character is a space, evaluating a condition to determine whether we're entering a new segment, possibly incrementing the counter, and updating the in underscore segment flag. Each of these operations is O(1), meaning their runtime does not depend on the size of the input. When you multiply the number of characters, n, by the O(1) operations for each, the result is O(n) for the entire algorithm. If we consider different scenarios, the best case occurs when the string is empty, as no iteration happens, resulting in O(1). For strings with a mix of spaces and characters, the loop still processes every character, giving an average case of O(n). In the worst case, when the string has no spaces, such as ABCDE, the loop still iterates through every single character, so the runtime remains O(n). Now let's focus on the space complexity. The algorithm has a space complexity of O(1), and here's why. First, it operates directly on the input string without allocating additional memory to modify or store it. The memory usage comes solely from the variables employed during the computation. These include the integer variable count, which tracks the number of segments, the Boolean variable in underscore segment, which monitors whether the current character is part of a segment, and the temporary character variable used during iteration. Since these are scalar variables, they require a fixed amount of memory that does not depend on the size of the input string. Therefore, the algorithm's memory usage remains constant, or O(1). If we compare this to a naive approach, such as using Python split method, the difference becomes clear. The naive approach splits the string into a list of substrings and then counts their number. While this is simple to implement, it introduces significant overhead, as the split method creates new substrings and stores them in memory. This increases the space complexity beyond O(1). Let's evaluate the time and space complexity of the naive approach for comparison. The split method iterates through the string to locate spaces and construct substrings, which gives it a time complexity of O(n), similar to the current solution. However, there's additional overhead in creating and storing these substrings, which can make it slower in practice. On the space complexity side, the split method creates a new list containing the substrings, requiring k space, where k is the total number of characters in all segments. This is in contrast to the current solution, which does not allocate memory for substrings and has a space complexity of 1. This makes the current solution more efficient in terms of memory usage. Mathematically, the current solution's time complexity is n, because it performs a single traversal of the string, and its space complexity is 1, because no additional memory is allocated. There are no nested loops or recursive calls, each operation within the loop is constant time. Overall, the current solution is both time optimal and space efficient compared to the naive approach. When tackling this problem, there are several common mistakes to watch out for. First, misidentifying segment boundaries is a frequent issue. This happens when multiple spaces between words or at the start or end of the string are not handled correctly. For example, in the string hello world, there are only 2 segments, but a naive implementation might count extra ones due to the spaces. Another common pitfall is relying on space-dependent splitting methods, like directly using the split function without validating edge cases. For instance, an empty string or a string with only spaces could lead to unexpected results, as split on an empty string returns an empty list. Additionally, some people overcomplicate the brute force approach by adding excessive checks for each character, which unnecessarily increases code complexity and makes debugging harder without any meaningful improvement. Performance is another area of concern. Using nested loops or operations that result in n squared complexity can be problematic for large inputs. Efficient solutions should aim for n. Finally, neglecting edge cases like an empty string, a string with only spaces, or a single word often reveals boundary issues in your implementation, so it's critical to test thoroughly for these scenarios. This problem offers valuable insights for interviews as well. First, it reinforces the importance of pattern recognition. Segment or token counting is a common theme in string processing problems, so mastering techniques for handling spaces, delimiters, and boundaries is essential. Optimization is another key focus. While a brute force method might suffice, demonstrating awareness of edge case handling and proposing linear time solutions can highlight your problem-solving skills. Communication is equally important. Interviewers often evaluate your ability to clearly explain how you address edge cases and articulate your thought process. Furthermore, this problem lends itself to generalization. It can be extended to scenarios involving different delimiters, like commas or semicolons, or even filtering criteria, such as counting only segments that meet a minimum length requirement. Related problems can also deepen your understanding. For example, LeetCode 58, which focuses on finding the length of the last word in a string, shares similar string parsing techniques. Another example is LeetCode 186, which requires in-place manipulation of words in a string, emphasizing careful boundary management. Building on related problems, LeetCode 151 is another excellent example. It involves reversing the order of words in a string while managing spaces, an extension of the boundary handling skills we discussed. Of course, LeetCode 434 itself is a direct variant of this problem and serves as an excellent practice opportunity. Now, when considering alternative approaches, several come to mind, each with its own trade-offs. A brute force approach involves manually iterating through the string, using flags to track when a segment starts and ends. While simple to understand, this method can require more code. Alternatively, you can use built-in functions like split to break the string into words and count the segments. This approach is concise and efficient but requires careful handling of edge cases, such as trimming spaces. Regular expressions are another option, using something like refindAll or \s+s to match non-space sequences. This method is powerful and concise but introduces dependency on regex, which might be unnecessary for simpler problems. Lastly, the two-pointer technique offers an efficient and elegant solution by dynamically defining segment boundaries as you traverse the string. While slightly more complex to implement than split, it balances performance and clarity effectively. Each approach has its merits, so choosing the right one depends on the problem constraints and your familiarity with the techniques. Great job! Today, we tackled problem number 434 and explored different approaches to solve it. We reviewed key concepts like string parsing, time-space trade-offs, and edge case handling. Keep practicing these techniques to strengthen your problem-solving skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!